My name is Yanjun. I'm a graduate student at Caltech, and today I'm going to share you some results from some recent NuSTAR and XMM-Newton observations of two new black hole X-ray binaries. So just about the sources I'm going to talk about today. The two targets are MAXI J1631 and MAXI J1820. So these are two new transient galactic black hole binaries discovered by MAXI when they went into outbursts. These are pretty bright targets. During the peak of the outburst, the flux level reaches to the level of about 2.5 crab and 4 crab. So they were pretty bright sources. And just a little bit about the background of these two targets. For MAXI J1631, because the source lies very close to the galactic plane, the absorption condensity is pretty high, and therefore there's no optical counterpart confirmed. And for J1820, the absorption condensity is pretty low, and the donor star was confirmed, and there's already a black hole mass measurement. So it is dynamically confirmed as a black hole binary. And because the outburst was very bright, it was well covered by radio, all the way from the radio to the X-ray band. There are a number of publications already on this source, and the data looks great, but I'm not going to talk about them in any detail, just for the background. So I asked for several NuSTAR and XMM-Newton observations of these two sources last year. In a lot of ways, of course, they share a lot of similarities because they are black hole binaries, but also just based on the data that we get, based on the features that we observed, they also tell us something different, like about different aspects of the accretion flow that's happening in these systems. So I'm going to go through these two targets as two case studies. Let's look at the first one, J1631. I asked for two NuSTAR observations during the brighter phases of the outburst, and they caught the source at two different accretion states. As we know, the X-ray the spectra of black hole binaries are mostly made up of two components. On the soft energy band, there's this component that is thermal emission from the accretion disk, and on the hot X-ray band, there's a parallel component that is believed to come from non-thermal emission from the coronal around the black hole. And for both states, I first fit the spectral with this very simple disk black body plus parallel model. And as we can see in the residuals, there are very clear relativistic disk reflection features showing the residuals. That is a broad INK line centered around 6 to 7 keV with a red wing. And there's also a constant reflection hump peaking at about 20 to 30 keV. And what makes this data set interesting to me is that with the high signal noise ratio spectra, we can actually see very clearly there's variation in the broad online profile during the two accretion states. Like on the left panel, as we can see, the line profile appears to be broader and stronger for the disk dominant state. And also there's a very large change in the flux of the ion line. The ion line appears to be much stronger for the disk dominant state. And also, the flux of the ion lines does not correlate positively with the flux of the parallel component. And there's a difference with a factor of 50. It is kind of unexpected because we would normally expect a positive correlation because the traditional view is that the ion lines are caused by the reprocessing of the coronal emission by the accretion disk. So normally we would expect it to be a positive correlation. So the question now is how we explain the very strong ion line during the disk dominant state. We need to think of a disk coronal geometry for this to work. So the first possibility that we think of could it be light bending? Because as the corona becomes more compact, the GR effect is going to bend more light onto the accretion disk. As we can see on the left panel here, therefore we are going to see more ion line flux. But in this case, a variation of a factor of 50 would be very difficult to explain just using light bending model. So the alternative is that we can think of, because for the disk dominant state, the disk component is the dominant one all the way to the hot X-ray band. So we need to think of is the reprocessing of the thermal disk photons in the hot X-ray band important for the reflection process. So the possibility we can think of is that some of the high energy disk photons goes into the surface layer of the accretion disk, and it interacts with the gases in the surface layer and also produce some of the ion line. In order to test this scenario, I fit Spectral in the disk dominant state with the REF-BHB model, which the model itself self-consistently includes a disk component when making the reflection spectra, and I can get a pretty good bet. But for the power component, we don't need to do that because we can treat the disk component separately, because it's not important for the reflection process. So that's kind of easier. And based on the spectral modeling results, I measured a pretty high vacuum spin, and the inner disk is consistent with the radius of the ISCO for the disk dominant states, while for the power dominant state, the disk is measured to be inner disk is measured to be truncated at about 12 Rg. So, and it's also interesting that the X-ray luminosity at the two accretion states are actually pretty similar. So we think whatever is triggering the disk truncation here is not caused by a change like in the general accretion rate, but it's caused by some disk instabilities associated with high accretion rates. So let's talk about the second case, J1820. And likewise, I asked for 2 observations with NuSTAR and XMM-Newton for this source, but this time I observed it during the faint phases of the outburst. That is when the main outburst already ended, and there was a very mini brightening period after that, before the source completely goes into the quiescent state. So again, we have fit the spectral with a very simple power model because the disk component here is too weak to be seen. We can still detect very clearly there are disk reflection features in the spectral residues. And this time, the ion line appears to be much narrower, as we can see here. And also, similarly, we see a clear variation in the ion line profile at the different phases of the outburst. As the luminosity drops, the width of the ion line gradually decreases. So this tells us that the ion line is produced at a larger radius from the black hole. And also from the timing properties, the frequency of the QPO decreases as the luminosity drops. We know that the QPO is generated in the optically seen comptonization region. So although we don't know what exactly caused the QPO, I think it's still an open question, but I think the bottom line is that the QPO is associated with some kind of characteristic timescale in the accretion flow. So this tells us that as the luminosity drops, the optically seen comptonization region increases in size. So now the question is, how do we explain the narrow ion line? What is the disk coronal geometry that we need to explain it? The first possibility we can think of is that there's a change in the coronal geometry. That is, a coronal increases in height. So it's going to illuminate more of the outer part of the accretion disk. Therefore, we are going to get a narrower ion line. And the second case is, as I plotted on the right hand, is the disk become truncated when the accretion rate is very low. So the inner edge of the accretion disk recedes from the central black hole, and the most inner part of the accretion flow is replaced by some optically thin accretion flow. And another factor that we need to consider is that when modeling spectra, we see that the reflection fraction is pretty low. It's about 0.1. So in order for the the scenario on the left-hand side to work, we need the corona to be significantly beamed away from the accretion disk. Even when the outburst was almost ending, so the target was almost close to the quiescent state. So that kind of make it seems to be unlikely to me. So well, for the disk truncation scenario, the low reflection fraction can be explained because the current factor of the disk is lower than typical value. So I performed my spectral modeling under the disk truncation scenario. And when combined with the results from the bright phase of the outburst, it shows that the inner disk start to recede from the scale below 1% of the Eddington ratio. And the disk truncation radius is measured to be like a few tens to a few hundreds of RG. And also the spectral modeling results agree well with the timing results. That is, if we use the lens serving processing model to infer the inner disk radius from the QPO. So it's kind of nice that these two arguments agree. I think what I have learned from my analysis of these two targets is that we can now confidently and clearly detect variations in the outline profile with NuSTAR now, like during different phases of the outburst of a galactic black hole binary. And it is also clear that they are direct indications of changes in the dynamics of the inner accretion flow around black holes. And they carry detailed information about the radiation process around black holes. And in order to explain what we observed from the timing and the spectrum features, we need to think of this coronal geometry. And usually we can like come up with different geometries that might possibly work. So it's not necessarily a unique one. But I guess that's also what makes it interesting in some ways, because it's still worth discussing, and there are different ways that might work. So I just end here and take questions.
Wonderful. Thank you very much.
Right. So if we have any questions, please go ahead and add them to the Q&A, and I can pass them along. I'm Ryan Hickox from Dartmouth College, by the way. I have one question to go. Here we go. Aaron Cara asked us a question. What was the radio doing during the time of the NuSTAR observations and the return to the low hard state in J1820?
I actually don't know. I don't know if they have observations during the time when the source was already pretty faint. So I'm not sure about that.
Great, thanks. Damien Christian asks, thanks. Did you see any features below 5 kV that some old Einstein observations showed some 3.5 kV feature?
For which source, Mike?
Oh, good question. Damien, can you clarify that? GX51?
No, we don't see. There's no clear indication for any like features at 3.5. There's no strong features at 3.5.
So thanks. So Kenichi Nishikawa asks, and this is, I guess, related to Aaron's question, do you observe jets? And I'm presuming this is in either one of these sources. Do you have any evidence for jets beyond what you've shown so far?
I don't analyze a radio data. That's something interesting for me to think of. I think there should be jets normally for the hard state, but I'm not sure how strong that's going to be, like when the source was already very faint. The jet should also be pretty weak. That's what my guess is, but I didn't check the radio data.
Thanks. I have a question related to the interpretation of the line widths and the QPOs. You mentioned that you had these, that we don't know what the origin of the QPRs are, the physical origin of the QPOs are in this system, or in systems like this. But you now have two bits of information about things that change in the state changes of this, or of the system, the width of the line and the QPO frequency. And so I'm wondering, is there some way to put those together to look at what the Doppler width of the line is, to actually place some constraint or rule out some scenarios for what potentially could produce those QPOs?
Yeah, I think it is possible to do that. I just tested one model for the QPOs, like the Lancerin precessing model, because a lot of people seem to agree that it is a very promising model for the QPOs. And just for this model, it seems to agree well with the spectral modeling results. So it is kind of good to know that. For other models, I didn't test them, but it's doable. And yeah.
And we have one more question from Knox Long, which is, in J1631, you saw a wind. Would scattering of light from the inner corona or disk off the wind affect the reflection signatures that you see in the outer disk?
Sorry, could you repeat?
Sure. So so you see this wind, and that you can see in the left-hand figure here. Would scattering of light from the inner corona or the disk off the wind affect the reflection signatures that you see in the outer disk in this system?
So the question is, would the disk wind affect the
does it produce scattering, I guess, that ultimately could then change the iron reflection features that you see farther out in the disk?
Yeah, I guess that's also, as you can imagine, it depends on the geometry. If the disk wind is usually along the disk plane, right? There's a very small angle, and well, if we see the view of the system almost like a face on, I don't think that's going to change a lot, because that's not going to obscure the live side. But if it's a very like edge-on system, I think that would be something that we need to consider.